So we're going to finish up the little part here in our notes about nomenclature. And then on Wednesday, we will continue on in our notes on bonding and get into some of that. So hopefully that'll be helpful for the lab part. So we're just going to kind of continue where we left off. So far we've talked about really type 1 and type 2 compounds. And really the differences between those two and really the similarities as well. So again, type 1 and type 2, they're both ionic compounds. That means they always will contain a metal and a non-metal. And as we talked about earlier, always the metal, which is really the most important one that you want to look at. Again, type 1 are guys that have a fixed positive charge. So again, those are our group 1, group 2, group 3, are zinc, cadmium, or silver from the transition metal region. And pretty much you just the whole name of the metal like we were doing, and IDE for the non-metal. Again, any additional metals or non-metals that you have in the formula, twos, numbers like that, we do not use prefixes ever in a type 1 compound. Type 2 is basically the same thing. It's also a metal, non-metal. It's also, again, the metal that's the most important, and that metal will be a transition metal. Are just to the right, like we've been talking about, like tin and antimony and lead. Those guys, really what makes them different is they do have the ability to make different positive charges depending on the situation. And because really they can make different positive charges, we do need to tell the person that's looking at the name which one we're talking about. Like in this case, we're talking about copper with a +1 charge, or we're talking about copper with a +2 charge. And the way that we do that is we use Roman numerals, and that's really the only additional thing that we do for the naming. Again, we still use the whole name of the metal. We use a Roman numeral to indicate the positive charge on the metal. And again, like we've been doing with type 1, ID at the end for our non-metal. And again, doesn't matter how many metals you have, doesn't matter how many non-metals you have. There's no prefixes at all in any type 1 or type 2 naming. It is not the correct place to use a prefix for sure. Any questions on any of those things we were just kind of finished up talking about? Also, as we saw here, if you're going from the name back to the formula, you really just want to think about the basic units that make those things up. What is the basic guy that has a positive charge? What is the basic guy that has a negative charge? And we do want to put it together again, really in the simplest way that will get you to 0. There's many ways you can put it together to get yourself to a 0 charge, but it does have to be the simplest way, putting the positive and negative guy together to get yourself to a negative charge or 0 charge. Okay, so as we saw there, there are certain guys that do not require Roman numerals, and those guys again are group 1 or group 2 or group 3. And added to that, again, are also those 3 transition metals, which is zinc and cadmium, which will always make a +2 charge. And again, silver, which will always make a +1 charge. If you've got any of those guys that are metals in there, that is a type 1 compound. You really don't have to worry about sort of, if you have the formula, you know, what the charge is or anything like that. You just need to name the whole name of the metal and IDE for our non-metal. Everybody else pretty much outside of that, which as we were just talking about our transition metals, they definitely do need a Roman numeral. And again, a very, very common mistake, as I mentioned earlier, is people will think the Roman numeral means how many metals you have or something like that. But again, it is actually just what the positive charge is if you took one of the metals out by themselves. So let's do a few more here, which I'm not sure where they went. So let me just make some up here, I suppose. That would be good. Let us do CR CL2. Let's do bless you. Let's do MG3P2. Let us do ZN BR2. And why don't we do some formulas? So let's do some silver phosphide. Let's do iron 3 oxide. And let's do lithium nitride. All right, same thing, names on the left and formulas on the right here. Let's see how we're doing. So we want same approach. We take kilocure, that is chromium, which is a metal. That is a non-metal, which is Cl. The important part, again, always our metal. And when we look at the periodic table, we see chromium in the transition metal region. So that usually should tell us that we need to figure out the charge on it. So again, at this point, maybe not sure what the charge is. Looking at our non-metal, we should know the charge of that, which is -1 because it's group number 7. There are 2 of them, which means we do have 2 of them. So that's a -2. Again, to balance that out, that tells us that the chromium must be +2 in this case. That's pretty much all we need to figure out in this case. We will use the whole name of the metal, which is chromium. We will do a Roman numeral 2 for the charge that's on the chromium. And the Cl at the end there becomes chloride. So chromium, Roman numeral 2, chloride in that case. Question on that one there. Looking at the next one, which is Mg, magnesium, metal, phosphorus, non-metal. Our magnesium is group number 2, which should tell us it has a fixed charge of +2. Also should tell us we don't have to worry about Roman numerals in this case because it has a fixed charge. That means we could just proceed to naming it, which would again be the whole name of the metal. And phosphorus becomes phosphide, IDE, at the end of it. Again, the 3 on the magnesium has no effect on the name, so we don't want to do anything like tri. The 2 on the phosphorus has no effect on the name, so no dyes. Again, no prefixes at all, ever in an ionic compound name. Yeah. Any questions on that particular one there? Again, obviously, the reason for the numbers is to get us to 0 because our cation here is magnesium. That's a +2. And our phosphorus is a -3. So the common number is 6 between those two. So we need 3 of the +2s to get us to 6, and we need 2 of the -3s to get us to 6 to balance it out. Any questions on that one? Coming down here, we have Zn, which is zinc, and that is a metal. We have Br, which is bromine, which is a non-metal. Zinc is a transition metal, but it is one of those that has a fixed charge. So it's actually a type 1 compound, this guy, because zinc, no matter what the situation is always going to be +2. So that means all we have to do is go zinc and bromide in this case. So remember, zinc, cadmium, and silver, exceptions for our transition metals. They are really type 1 metals because they have a fixed charge. Any question on any of those 3 there? Coming to the right, when we're going to our name, we really just want to figure out what is the positive guy, what is the negative guy. So silver, also a transition metal, but one of those ones that we talked about that has a fixed charge. Silver's charge is +1. Phosphide is phosphorus on the periodic table, which is group number 5. And that means it should have a -3 charge. In this particular case, we would actually need more of the silver, right? To get us to 0, we need a grand total of 3 to do that. And that would give us Ag3 and 1 phosphorus. That basically means we have 3 silvers at +1 each, gives us a grand total of +3, and 1 phosphide at -3. So we're all balanced. Any questions on that one there? Iron, Roman numeral 3. So the Roman numeral 3 tells us this is really a type 2 compound. The Roman numeral 3 also tells us that the iron is the guy that has the +3 charge. That is where the Roman numeral is for. Oxide is oxygen on the periodic table, which is group 6, and that has a fixed charge of -2. Again, when we put this together, we want to equal 0. So the easiest way to do that is just to multiply those two numbers together, and that gives us 6 is what we're shooting for. So to get iron to 6, we actually need, I'll come this way, we need 2 of them, right? To get our oxygen to 6, we need 3 of them, and we end up with Fe2O3. 2 times +3 is +6, and 3 times -2 is -6, gives us a 0. Any questions on that one there? Lastly, we have lithium, no Roman numeral, nitride. So lithium is group 1, which means it has a +1 charge. Nitride is nitrogen, which is group 3. And in this particular case, we will need 3 of our lithiums to balance it out. So Li3 and 1 nitrogen there at the end. Any questions on any of these here? So always in an ionic compound, as we talked about a number of times, it is that metal that's really important. And it really does lead you to where you need to go. The nice thing really about ionic compounds is, other than the ones that need Roman numerals, there's not a lot of difference in how you name them. It's always the same sort of combination, whole name of the metal, and IDE on the non-metal. Again, the real decision is whether or not you're going to put a Roman numeral in it or not, and it depends obviously on the metal. Any questions on any of those? Okay. So here's sort of a decision tree of what we just talked about, type 1 or type 2. Let's talk about type 3 compounds. Now, type 3 compounds are different. Type 3 compounds are actually our covalent compounds, are molecular. These are our nonmetals together. So our 2 nonmetals together, these are the ones that are going to actually be sharing electrons here. So these are a completely different sort of compound in terms of how they are held together. These are guys that are actually held together by sharing of electrons versus what we were talking about previously. And by the way, before we go too far previously, let me just talk about one, which I think I might not have, transition metal, and that's actually mercury. And mercury is kind of a weird one. It's right there in that middle. This is Hg2+ with a 2 on the bottom, and this is Hg2+. As odd as it may sound, this is actually mercury 1. It's a dimer. It's actually 2 mercury 1s together, which is why there's a 2 on the bottom and the 2 on the top. Oddly, the one that has just the 1, 2 is mercury 2. So that's a weird one that you sometimes come across. How do you tell the difference between them is that 2 will oftentimes still hang around. So for example, if we had a formula of HgCl2 and we had Hg2Cl2, they look very similar. This is mercury and chloride. And in this case, this is mercury 2 chloride here. This is actually mercury 1, and we look down here, we can see the extra 2 that's there, and that guy again always hangs out, that 2, and that tells us that it is mercury Roman numeral 1 chloride in this case. So they both have a +2 charge, but that mercury 1 actually has that extra 2 on the bottom, and usually you will still kind of see it there when you put it together in a formula, and that's how you kind of know it's mercury 1 versus mercury 2. Kind of a weird one, mercury. But it does pop up occasionally, so sometimes it's confusing. Any questions on mercury there? And by the way, again, this is basically Hg2+ and Cl- for this guy. And this is Hg2+ and Cl- and Cl-. So again, the difference is that extra 2 on the bottom that helps you distinguish between mercury 1 and mercury 2. Okay. All right, that was a side note. Back to mercury, that's in case you come across it. But back to really type 3, which is completely different as I've been talking about. We have sharing of electrons here, non-metal together. These are absolutely 100% the easiest ones to do, but they're absolutely 100% the ones people screw up on the most because they think they got to do a whole bunch of weird things when they go to name these guys. So let's talk a little bit about type 3. Type 3 guys are basically will only contain nonmetals, and this is actually the place where we use prefixes. So this is the appropriate place to use prefixes. Well, basically, as we will see, we use basically the appropriate prefix and the whole name of the first element. Then we use the appropriate prefix and the nonmetal that comes second with the IDE. So this is absolutely where you should use prefixes. But again, there are a few rules to how to properly use the prefixes, which we're going to talk about here in a second. By the way, there are certain things that when a couple of nonmetals come together, as we talked about earlier, that we still use, again, those common names. So as we saw earlier, H2O, which are two nonmetals together, again, is still water. CH4 is methane. NH3 is ammonia. Now, when we have hydrogen involved, although hydrogen really is a nonmetal and you have hydrogen together with another nonmetal, even though that's really two nonmetals together, we really don't treat it or name it like a nonmetal situation. So sort of an exception to what we're going to be talking about here is when we put something like, for example, HCl together. H is hydrogen, which is a nonmetal. Cl here is chloride, which is also a nonmetal. It really follows type 1 naming when you are dealing with hydrogen. So really this is considered like H plus and Cl minus. So we would call this hydrogen chloride. So we really name anything that has hydrogen in front of it, even though, again, it's nonmetal, even though technically speaking, they are sharing electrons. It is named very much like a type 1 compound. Even if you had two of them, so if you have like H2S, this is basically two hydrogen ions and a sulfide ion. This would also be called hydrogen sulfide. So that's also one sort of exception that, you know, even though hydrogen is really a nonmetal and obviously the chloride in this case is a nonmetal, we really do treat it more as an ionic compound, even though technically it's not. It's sharing electrons, just the way it's named. And other applications like acids, we'll talk about a little bit later on, we sort of treat it almost like an ionic compound, even though technically speaking, there is sharing of electrons, it is covalent. So hydrogen is one sort of exception that if you have hydrogen that comes in front, it's hydrogen and whatever the negative guy name is with the IDE at the end of it. Other than that, all other sort of nonmetals and nonmetals that come together, we do follow these rules here with the prefixes that we're going to talk about in terms of naming it. So let's talk about sort of those rules. Basically, it is the first element that comes first, and we use the entire name, and the second element gets the IDE at the end of it. And we do use these prefixes. Prefixes like 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. We don't usually get that far, but yeah, that's usually where we're at. There are a few rules that occur with these prefixes. The first major rule is we never use mono on the first name, but we can use it on the second name. So we never use the prefix mono on the first name, but absolutely perfectly fine to use there on the second name. So for example, if we had CO, C is carbon, oxygen is O, and that is two nonmetals together. At that point, you should be really happy and go, it's just prefixes. You should be happy because you don't have to figure out charges. You don't have to figure out anything else. You pretty much just need to use the appropriate prefix of what is there. One carbon would be mono. One oxygen would be mono in terms of the prefix. Now, we don't use mono on the first name, so we would just use the whole name here, which would be carbon. Another consideration that occurs when we use prefixes is sometimes we end up with two vowels that back up to each other. So if we just strictly wrote it with the prefix mono and then oxide, we end up with two O's that back up to each other. In that situation, we typically will drop the O from the prefix, and this is what is commonly known as carbon monoxide, not monooxide. So this is known as carbon monoxide. So when we get a couple of vowels that back up to each other, like very commonly O and O, prefix O goes away. A and an O, the prefix A goes away. Actually, two I's are okay, but other than that, basically two O's together, we get rid of one of the O's, an A and an O, get rid of the A. We don't use, again, the mono prefix on that first one, but as you can see here, we could definitely use it on the second one. Any questions on that there? So here are our prefixes, as I mentioned earlier, and again, a couple places where, we kind of avoid that vowel. That's why if we had something like CO2, that would be carbon and oxygen, both nonmetals. One carbon means mono. We don't use it on the first name. That is how we get to the name carbon. Two oxygens, prefix is di. Second name gets the IDE after it. So that is carbon dioxide. And again, that is where we should properly use our prefixes. Any questions on that one there? Nothing to balance, nothing to figure out charges. You simply just write what's there with the appropriate prefix. This is where people screw up. They want to do like charges. They want to figure out Roman numerals, but there should be no Roman numerals here at all. It should only be prefixes here in this case. So other considerations, as I mentioned before, we will oftentimes drop those prefix vowels when we get them backed up. And these are the two common places, as we talked about just a second ago, A and O and O and O. We'll drop those prefix vowels so we don't get those weird names. Here's the guy we talked about where we do use common names. So again, this is not dihydrogen monoxide. This is not nitrogen trihydride. We'd use ammonia, water, and obviously CH4, which is methane. The simplest organic molecule you can have is common names you should go by. And as we talked about just a second ago, again, if you come across something that's basically hydrogen and something else, kind of name it like type 1 and like an ionic compound, even though it's technically non-metal. Any questions on those there? All right, so why don't we try some here, I think. So for each of these, come up with the proper name, and I'll change this one since I kind of ruined that one already. So we'll do N2O5. And then if we have some names, let's do sulfur hexachloride. Let's do carbon tetrabromide. All right, let's take a look. And again, like I said, these really should be sort of the easiest ones that you do if you don't overcomplicate it. So first off, we look at I2O7. I is iodine, which is a nonmetal. O is oxygen, which is a nonmetal. All of a sudden, that should tell you we're dealing with type 3, which means we don't have to worry about charges or anything like that. We pretty much just need to pick the appropriate prefix and write what's there. So the prefix for 2 is di. We use the whole name of that first element. So this would be diiodine. The two I's are actually okay in this case. The second guy, we would use the appropriate prefix, which is 7, which is hepta. And again, we would make IDE for the second guy. So that would be heptoxide. Here we would drop the A off of the prefix so we don't get that A and O that back up to one another. Any questions on that one? Same thing rolling down, we see nitrogen, which is a nonmetal, oxygen, which is a nonmetal. Again, we just got to roll with our prefixes. We got 2 here, which again would be di, whole name of the first element, which would be nitrogen. Prefix here for 5 is penta. Again, here we will drop the A so we don't get the A and the O that back up to each other. And this would be pentoxide in this particular case. Lastly, we see phosphorus, which is a nonmetal. We see Cl, which is a nonmetal. And we see 1 for our phosphorus, so that would be mono, but we do not use it on the first name. So in that case, we will just use the whole name here. So that is phosphorus. We have 3 for our Cl, so the prefix for 3 is tri. And again, the Cl then would get the IDE treatment at the end, and we would end up with phosphorus trichloride. Again, nothing really to calculate, nothing about charges or anything like that that we have to do. Any questions on those there? Now, when we have a name going to formula, as soon as you see some prefixes, I think is even super easier here. So we have sulfur hexachloride. Again, the prefix should tell us it is a type 3. No prefix on the first one should tell us it's mono and it's 1. So we just simply need to write an S. Hexa is the prefix for 6 and chloride is Cl. So it would be Cl6. And that is all they wrote. Again, nothing to balance on this one because it is nonmetal and nonmetal. Same thing here, carbon tetrabromide. When we see the tetra, it tells us it's type 3. No prefix here tells us we just have 1. So we would write a C. Tetra is 4, bromide is Br, and this would be CBr4. Any questions on that one there? Right. Now, the last one here that we fixed, we don't have oxygen everywhere, but we do see some prefixes. So di means 2, oxygen is O, so that's an O2. Penta is 5, sulfide is S. Looks something like that, yeah. Any question on type 3? Again, really the easiest, but it is unfortunately the ones that people really do sort of screw up on a lot. But just keep it simple. And this is absolutely the only place really you should be using prefixes is right here. You also should see in type 3, it's only prefixes, no Roman numerals, no nothing else, no combinations. So if you find yourself doing like a Roman numeral and a prefix, probably incorrect. Yeah, so just prefixes by themselves. Roman numerals by themselves are no Roman numerals like we did in type 1. Any question on any of those type of naming? All right. So just to review the 3 types of naming we talked about so far: type 1 ionic compounds, metal, non-metal, metal fixed charge, whole name of the metal, IDE for the non-metal. Type 2, metal and non-metal. Metal here, we need to figure out the charge, whole name of the metal, Roman numeral for the charge, IDE for our non-metal. And what we just finished up on there is our 2 non-metals together. No Roman numerals, nothing like that. Pretty much the appropriate prefix on both names. First guy gets the entire name, second one gets the IDE. We do not use mono on the first one, but it's okay again on the second one. The last type of naming we're going to talk about are ones that contain polyatomic ions. So polyatomic ions are basically guys that are held together by sharing of electrons, but they actually have an overall charge. So there are actually 2 things that actually are a polyatomic ion is something that actually is held together through covalent bonding. They are groups of non-metals together, but they actually do have an overall charge, and that makes them ions. So if we look at something like this, which is NH4NO3, this actually contains 2 different polyatomic ions. The guy on the left there is actually NH4 plus. And this is different than NH3, which is oftentimes confused for this guy. That 1 nitrogen and those 4 oxygens, they stay together. They move around as a unit. They have an overall charge of +1. What it basically is is this guy here, where the nitrogen and the hydrogen, they're all held together by sharing of electrons, but this whole thing has a +1 charge. So this whole thing always stays together, moves around as a whole unit. The hydrogens don't break apart from the nitrogen. It just moves around as one unit, and it has an overall charge of +1 in that particular case. The guy on the left there also is a polyatomic ion. The one nitrogen and the 3 oxygens are actually sharing electrons, but overall it has basically a -1 charge. Same thing here. This is basically looks something like this, and we'll talk about how to draw these later on, but it's basically this entire thing held together. They're sharing electrons. Those guys are never going to break apart from each other. The nitrogen and oxygens, they move around as one unit, just like I drew on the other page there, our NH4 plus. So it's an odd thing, a polyatomic ion. It's actually groups of nonmetals which actually share electrons and are covalently bonded together. But as a whole unit, it actually has an overall charge. So they do behave like ions. And that is why ultimately what we are putting together here is something that has a +1 charge and something that has a -1 charge. So those are two things with charges, which means it needs to equal 0. And that's why when we put it together, we get the formula that we see up on top, which is NH4NO3. Any questions on that so far? Now, these polyatomic ions have special names. This is what is known as the ammonium ion. This guy here is what is known as the nitrate ion. The good thing about polyatomic ions is you just use the name. So when we put it together, this is what is known as ammonium nitrate. So when we are dealing with polyatomic ions, we basically just use the whole name of the polyatomic ion. It's kind of like really, when we're dealing with polyatomic ions, they really do follow kind of type 1 and type 2 naming that we talked about. They're really ionic compounds. The other thing that really happens with polyatomic ions is, for the most part, this is one of the few positive guys you'll see. Most polyatomic ions are negatively charged, and most polyatomic ions will end up with a metal that's positively charged. So a lot of what we do is we bounce back to our normal sort of type 1, type 2 rules. And if the metal needs a Roman numeral, put the Roman numeral. If the metal doesn't need a Roman numeral, we don't put the Roman numeral. So for example, if we did NaNO3, this is our still polyatomic ion, which is nitrate, that has a -1 charge. It is now together with our sodium that has a +1 charge. So we would still look at the metal here, and sodium is group 1, so it doesn't need a Roman numeral. It does not. It has a fixed charge, like we talked about with type 1, which means if we were to name this guy, this would be sodium and nitrate. So no need for a Roman numeral. We just use the whole name of the metal and the whole name here of the polyatomic ion. If we had, if we put, let's see here, we'll do this guy, CuNO3 for now. Cu is copper. That is a transition metal, right? Which means it could have multiple charges. So we do need to figure out the charge, and it should use a Roman numeral. We would do the same thing when we know about nitrate. It has a -1 charge, which means the copper in this case should have what type of charge? It has to have a +1 charge to balance out the nitrate charge of -1. So this would be called copper, just like we did with type 2, Roman numeral 1, whole name of the polyatomic ion, which would be nitrate. So 9 times out of 10, you're going to find a polyatomic ion that's going to be attached to a metal, and you would really follow type 1 or type 2 rules for it. And you basically would use either a Roman numeral or no Roman numeral, depending on the metal, and the whole name of the polyatomic ion. Any questions on that there? There is a wonderful, terrible list, such as one of these. The best way to learn the polyatomic ions, unfortunately, is to memorize it. Yes, so there are a couple ways that you could help yourself memorize these. First off, most polyatomic ions will end in ate or ite. There are groups of like 2 that are related to each other, like SO4 2 minus, SO3 2 minus. This is the sulfate ion. This is the sulfite ion. If you look at NO3 minus, like we just talked about, that is nitrate, and NO2 minus is also related. That is nitrite. The one that typically has the most oxygens in a group of 2 that are related to each other will end in ate. The one that has the least number of oxygens will end in ite. Good way to think about that is I ate too much, right? The most oxygens, right, is the one that has that. Unfortunately, as well, there are some groups of 4 that are related to each other, like we see here. This is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Every single one of these has a -1 charge. Again, the Cl and the oxygens all stay together. If we break it up right about here, to our left are the guys that have the most oxygens, which means they both should end in ate. So this guy here is chlorate. This guy here would also be chlorate, but we obviously can't have the same name for 2 different things. So when you have a group of 4, the one that has the most oxygens ends in ate, but also starts in per. So that is where the name perchlorate comes from. The guys to the right here have the least number of oxygens, which means they should end in ite. So this guy here would be chlorite, I-T-E. This guy here would also be chlorite, but just like before, you can't have obviously the same name for 2 guys. So in a group of 4, the one with the least number of oxygens will end in ite and also start with hypo. So that is hypochlorite, chlorite, chlorate, and perchlorate. You could actually substitute the Cl for anybody in group 7. So if you had BrO3 minus instead of chlorate, this would be bromate. So you could actually substitute those guys out. The other common thing that you will see is sometimes we will put a hydrogen or an H plus in front of somebody on the list. So for example, if we look at CO3 2 minus, that is 1 carbon, 3 oxygen with a -2. That is what is known as carbonate. If we put a H plus in front of it, that will be HCO3 minus. We put an H plus, which means hydrogen carbonate. Or sometimes people refer to it as bicarbonate. Sometimes people will use the bi instead of hydrogen, and it'll be called bicarbonate. We see that with sulfate as well. Here's hydrogen sulfate and bisulfate. So those are some common old names that are sometimes used. Not every single polyatomic ion will actually end in ATE, like over here. That is OH minus, which is hydroxide, IDE. There's cyanide, which ends in IDE. But the best way to do it is you got to kind of memorize it, both the name and the charge and the formula, so you could put them together correctly. Here's another table and another one in case you're curious as well. So let's take a look at some of these here just to see how we typically will see them. So for example, if we'll go maybe this table here. So let's say we had Fe NO3 2. So we would look at this and we want to identify what we got going. This is obviously a metal and this is a polyatomic ion. So we want to kind of approach it the same way as type 1 or type 2. First off, does iron need a Roman numeral? Iron does need a Roman numeral. It's a transition metal. So we want to really approach it the same way. We don't know what iron's charge is, but when you learn this list, you will know, as we saw, that nitrate has a -1 charge, and there's not one of them, but there are two of them, which means the overall negative charge is -2. That means that the positive charge on the iron would have to be +2, just like before, to balance it out to 0. And we would name this, like before, iron, Roman numeral 2, because of the charge. And just like type 1 and type 2, even though there technically are two of these nitrates, it does not affect the name. So we just use the whole name of the polyatomic ion, which would be nitrate. Any questions on that there? So what would CaSO4 be? What would that name be? So if we start with it, let's start with calcium, which is a metal, doesn't need a Roman numeral. It does not, because it's group 2, it has a fixed charge. So we could just do what we did before and go calcium. We would then look up this guy, which is sulfate, and use the whole name here. This would be calcium sulfate in this particular case. Question on that there. So let's take a look at, let's do, why don't you write the formula for copper, Roman numeral 2, let's do hydroxide. Okay, let's take a look at, we want to approach the same way. So copper, Roman numeral 2 means copper has what type of charge? Has a +2 charge, right? That's what the Roman numeral means. Hydroxide, once you learn it, you'll go to the list, you'll memorize it, you'll know that it is OH-. So basically, we were putting together something with a +2 and a -1, which means we need more of the copper or more of the hydroxide. We do need more of the hydroxide, just like before. We would need actually two of them, right, to balance it out. Now, when we write the formula, this would be CuOH and 2. If I write it like that, is that correct? The answer is actually it is not, because what that formula says is I have 1 copper, 1 oxygen, and 2 hydrogens, when in reality, I actually have 1 oxygen, 2 oxygens. So whenever you have more than one polyatomic ion and you're writing the formula for it, you do have to put the parentheses around it with a number on the bottom to indicate that you have 2 of those hydroxide units. And now what that says is that I have basically 2 oxygens, right? If we multiply that in, and 2 hydrogens, which is exactly what we got going on there. So a really important thing is sometimes you will end up with more than one polyatomic ion. You do have to put parentheses around it and put the 2, whatever the number may be, which is what we did here, right? In this case, we needed 2 of the nitrates. We needed to put the parentheses around it and the 2 on the bottom. Question on that there. So polyatomic ions, you do have to kind of memorize them, the names and the formulas. As you can see here, regardless of how many you have, you just use the name of it. So we had 2 hydroxides. Again, we don't do dihydroxide or anything like that. No prefixes. We just use a name. There are some actual polyatomic ions that actually do have a prefix. You do keep those because that's part of the name. But that's the only place that you would technically have like a Roman numeral and a prefix together, is if one of the names of the polyatomic ions actually has a prefix in it. Other than that, again, you shouldn't be using prefixes if it's not part of the polyatomic ion name. Now, like I said before, pretty much 9 times out of 10, you're going to have your polyatomic ions going to be negative, and it's going to be hooked up with a metal. So you really can fall back to our type 1, type 2 sort of rules for the metal. And really all you have to decide is, you know, do I need to put a Roman numeral with that metal or not, just like you would do with type 1 or type 2. And again, no matter how many polyatomic ions you use, just the whole name of it. The only additional thing you got to watch out for is formulas. Got to put the parentheses around any polyatomic ion that you have more than one of. Any questions on polyatomic ions here? All right, so that's a nice little naming wrap up there.